Hello, everyone. Do you hear me? And do you see me?
Yes, we do.
Yes. Okay.
Yep.
Perfect. Thanks a lot. So, welcome to this course on machine learning. This is actually part of a joint effort, if you want, for the students coming from Valencia and students coming from Madrid. And so we'll try to manage all these all the attendees. And please, if there is any questions, I please ask you to just unmute yourself, because I am not too familiarized with all these systems, and then I may miss your question if you post it in the chat. So I prefer just to unmute yourself and interrupt me, since this is supposed to be informal. Okay. So this on the one hand. On the other hand, I've been told to stream this on YouTube. So this is some experiment I'm doing today, and this if this works, I will tell you tomorrow about it. But you're supposed to interact with me only via this channel, via Zoom. Okay. Okay, so let's start. Let me share screen. You see the screen here?
Yes.
Okay, so there is some notes I would like to some remarks I would like to share with you before. So first of all, about the format and the scope. As I was mentioning in the description of the course in the Indico, these lectures are actually normally will be Blackboard quotation, because this is online, so this is going to be via tablet, except for the first part of this first day, which is going to be just some slides I will show you. But in general, it's going to be like some Blackboard based, if you want. And also there are two hands-on sessions conceived for in these dates that require you to work with the computer together with me. And I mean, as for the scope, I mean, this is a general purpose course, so it is will be hopefully useful regardless the area of physics that you work with, and being high energy physics or condensed matter or whatever. It should be able to help you in your research. And for the some requirements, please note the following, that I am assuming here that you have a minimum knowledge on statistics given from some course, previous course. I gave before Eastern, I gave some course on statistics in Valencia, and recently also here in Madrid. But it doesn't have to be this one. It is just I am assuming that you're familiarized with many terms that I will be showing. And in any case, the second part of this lecture is going to be like a summary of statistics, like a minimum summary that would be required for continuing with the lectures. Also note that for those of you requiring some marks, some credits from your university, like it is the case for Valencia, please, I mean, you do your homeworks, because this is the way I will have to, I will have for evaluating your progress and for giving the certificate. And also, you should also be familiarized with Python, in the sense of all the codes I will show here are going to be based on Python. And in particular, the hands-on sessions will be Python notebooks given by the, that you can do it locally if you want. But you could also use Google Colab which is a web-based platform. I mean, it's for Python notebooks if you want, but this is going to be for the hands-on. So, okay, this on the one hand. On the other hand, the bibliography. Okay, there are many books out there in the market, and there are also many very good web pages that nicely introduce these topics, etc. But the two main books this course is based on are these two ones I'm showing here. The first one is by Bishop, which is probably the most popular book among data scientists, which is this pattern recognition and machine learning. The other book, it is also becoming very popular recently. It is more recent than the one from Bishop, and it is these elements of statistical learning by Hastie and company, and which is actually giving another structure, another approach to, but it is the same idea of statistical foundations of machine learning. In particular, the first one, Bishop. So this, the Bishop was a physicist. At some point, he changed field, and then he became an authority in machine learning community. So it is a book that it is at least for me, it is not natural to read because it is like in the flow of a physics book, let's say. Anyway, so let's start without more delay. Let's start with the first part of this lecture. This is going to be an overview, an extended overview, and you're not supposed to fully understand what I'm saying here. You're just supposed to take this as a magazine, okay? Just watch what I'm trying to tell you here, and everything I'm trying to tell you here, most of it will be treated in detail during the lectures. So it is just for you to have this extended overview or an idea of what will be covered during the lectures. But please don't be stressed about not understanding some slide or so. Okay, so let's start then. The outline of this first slide, let's say, is okay. I will just briefly go to some definition and history of machine learning, the main paradigms of learning, and then I will go in a little bit more into detail of what is supervised learning and unsupervised learning, let's say, which are two of the paradigms. So actually, definition of machine learning is challenging in the sense that okay, it is actually a discipline which is a multidisciplinary discipline, and it may have many definitions, but probably the most probably formal definition I have found is this one by Mitchell at the late 90s, which is a computer program is said to learn from experience, E, with respect to some class of tasks, T, and perform a measure. You need to perform a measure of performance, right? And this performance will improve with experience, let's say. So this is very abstract and very in the lines of computational learning theory, which is the foundations of machine learning at some point. But this more or less covers what the process of learning that we are actually implementing in machine learning. So, but anyway, an exhaustive definition of machine learning may contain, if you want, these terms. So of course, this is a subfield of artificial intelligence. So it's not only the robot, but what is the algorithm behind the robot arm that is performing some task, okay? And there is if you want, it is founded by the basis of this is this computational learning theory, which is theorems about what does it mean to learn. So it is a formalization of what does it mean to learn something, to learn some concept, if you want. And this computational learning theory was very popular in the 80s. Nowadays are less used in practical machine learning, except for the quantum machine learning, which is not the topic of this course. And there is also, of course, machine learning is about statistical inference done by a computer. And you need to study this, all these statistical models that you develop in order to describe some data. And it is also an important keyword or key phrase, if you want, is generalized from experience, in the sense that you should be able to take some data and be able to predict the the behavior of the new data point, if you want, or the new event that comes. And of course, it has to do with pattern recognition at some point, image recognition or pattern recognition in general. And this is a Venn diagram that is not, I didn't do myself. I just took from the literature, and that nicely shows what is the, if you want, that machine learning is actually this interplay between statistics and computer science. No, so you have like very complicated, potentially very complicated statistical models that are very hard to compute or to solve, and for that you need some computer science behind that allows you to implement this in an automated way, if you want. Okay, right. So as for the history, okay, this is a for sure biased history on machine learning, but let's say that probably it all started in the 40s, where Alan Turing quote, "What we want is a machine that can learn from experience." So we wanted to perform some task, some learning, some automated learning, if you want. Of course, then all of this gave rise to many ideas about how to implement this, and probably the first model actually was the first neural network that was created was in 1951 by the Air Force Office in the States. Then at some point later after, there is a nice paper to read. Actually, Arthur Samuel wrote this paper about designing a computer program to play checkers game, and this was in the context of IBM research. And then the late 50s, the perceptron, which is some model that we are going to cover in these lectures, was created at Cornell. 10 years later, you see this nearest neighbor algorithm, which is a very nice, very simple but powerful algorithm for pattern recognition and for classification was invented. And actually, the motivation behind was to create these map routes. Then the backpropagation in the 70s was invented. Backpropagation is a technique to, let's say, to solve or to minimize your functions, let's say, to train. No? You do it through backpropagation. Well, other relevant items here, for example, in the 85, a program that learns to pronounce the words in the same way that baby does, or reinforcement learning, which is something very popular nowadays, that was created many years ago, already in the 89. But actually, it was invented, but it became like practical, so that you actually could implement it. Because what happened with machine learning through history, or the early history of machine learning, is that there were a lot of people developing these methods, but they were unfeasible to implement or let's say, intractable in a computer. And that's why you see many algorithms that were rescued from 40 years ago, and now they are able to be implemented because the computer power grows, and then this became possible. And then, of course, now more recent, or a little bit more recent, if you want, in the late 90s, IBM Deep Blue that beat Kasparov in a chess game. That was a very important news in all this world of machine learning development. And okay, to 2012, they were actually able to recognize cats on YouTube by this Google Brain team that was already created some many years ago. And a big name on this was Andrew Ng, which is actually the author of many open courses in the internet. And more recently, Google Alpha beat an unhandicapped professional human Go player. Of course, Go is like it's even more difficult than chess, and probably the state of the art in Go is behind the state of the art in chess. But I mean, this is more or less what has been happening in the last years. Okay, so as for the machine learning paradigms, so here, let's say that the first and probably most popular and most used learning paradigm here is supervised learning. And supervised learning is something that allows you to make inference, because let's say that you know already the answer that you should get for some set of points. So in that way, it is supervised because you have some idea, you have some previous idea of what to get, and then the only thing you require is to do some extrapolation if you want. And this is actually related to a computational learning concept, which is a method called probably approximately correct, this PAC thing. And you may search if you are curious. And the whole idea is the following. So you can frame this task of supervised learning, or you can format, if you want, your data set as an input X here and an output Y. So imagine that you have some number of variables that describe your system, like 3 variables, let's say. So you may have 3 columns of n data points, or d columns of n data points. This is for the input variables. And these 3 variables, let's say, you use these variables to predict the value of other variables given by this output Y. And in general, there may be k outputs for the same input if you want. So you have this data set in this format of a matrix, if you want, of an array, of 2-dimensional array, that allows you to perform this learning. And the task here is to make a statistical inference on the distribution of data. What I'm saying here, statistical inference, is what you are after is the underlying distribution that generated this data. So this is the essential task. And as a second task, of course, what you want to do is to predict the output for a new point. So in the case of a regression, so you have here a continuous variable, and this continuous variable so may have simplified the behavior like this one, these blue data points in the left. And after you, let's say, model what was the underlying distribution of these data points here, then you are able actually to predict the value of a point, of a new point here at around 15 or so. Okay. And in the case of classification now, what happens here is that the task is to being able to discriminate the points like belonging to a class or the other, like signal background, or monkeys versus cats or something. And here you are also trying to estimate, if you want, the underlying distribution of this data, behind this data. And as a second step, you may be able to predict what was the class, for example, of this red point here. As opposed to this, there is a second learning approach, learning paradigm, which is called unsupervised learning, where data here only contain inputs, if you want, not outputs or labels. So it is like in this plot here of classification. Imagine that you have this plot, but you don't know the labels, you don't know the classes. So for you, all of the points look like the same. And the idea here, well, this is one of the tasks for unsupervised learning, is that this unlabeled data, what you would like to do is to clusterize it at some point, to say, okay, I don't know the labels, but it seems to be that those points belong to this group and those points belong to this other group, etc. So there is some sort of clustering algorithm that you are after. So this is the first task in unsupervised learning. Other task in supervised learning has to do with the fact of with the task of the problem of dimensionality reduction, in the sense of, for example, imagine you have this two-dimensional data here at the bottom left, and this two-dimensional data here. Okay, you may say, okay, probably if I only keep one dimension, this one dimension, if I choose it correctly, would actually describe reasonably well my data, and I don't need to then to cope with all the original dimensions. So this is a problem that is very useful when you have high dimensional data sets that are difficult to handle, and this is something that has to do with the let's say the correlations between all these dimensions, between all these features. Features here refer to the input variable. So each input variable is a feature of the set. And a final task for unsupervised learning is the task of estimating the probability density behind some points. So let's say that you have in one dimension, imagine that you have all these points at the bottom of this plot here. And then you have this sample of points, and then you want to say, okay, what is the generating probability distribution of these points? And this you also do with the supervised learning, let's say, like kernel density estimation, etc. There is a third big, of course, there are many paradigms, but I'm talking only about the most important ones. There is a third important paradigm, which is reinforcement learning, which is actually similar in spirit to what we humans learn from our environment, in the following sense. So there is some computer program here called agent that performs like an action to the environment, and this action may have some reward as a result of that. And depending on the reward, you query again, or you make another action to the environment. So there is this loop here that is typical in reinforcement learning that allows the agent to learn the environment. So this is commonly used for learning to play games like chess or Go. It is typically not used in physics applications, but there are, of course, some papers here and there that used it. And here the environment is whatever. It is, for example, the physical world in which a program operates. For example, in this case of playing games, it's like, for example, the state in the tic-tac-toe game, for example, or state in the chess game. And of course, the action you do it, so given by a policy, which is a method to map the program state to the action. So depending on the state I am, I will perform some action. So this is like the policy that you need to define. And then you have, you perform your action. So what is the action to move to a particular new state of the system, of the environment. And then you have your reward, which is the feedback, which is typically, for example, a cost function. If I have as a result of my action, I have a cost function, which is very bad. So I learned that this was a bad move, let's say. And of course, the opposite. So let's go a little bit more into details about supervised learning. It is important to note here, and this is something I always tell, that a model here machine learning refers a priori to the specification of a distribution function. So it is the same as in statistics, where you say I'm specifying a model. What I'm specifying is the statistical model a priori, which in other words is to say, okay, this data, I will, for example, assume it comes from some distribution here, exponential distribution or Gaussian distribution or whatever. So if the distribution, once you assume the distribution, if you want, then the model, when you specify the model, it will refer actually to model the expected value. Sorry, something happened here. I don't know. Do you still hear me?
Yes.
Yeah.
Okay, I don't know what happened. Something came up to my computer, but okay. If you hear me, then everything is well. So what I was saying is that more typically, let's say a model is referring to the expected value of some output variables, as we do in physics, actually. For example, imagine that your observable, you are assuming it is following a Gaussian distribution. So you see the Gaussian distribution here of observable y, and then the mean of the Gaussian distribution depends on also on the input, of course, x, and of some parameters, w, some number of parameters that I put here in a vector w. So in physics, what we do in physics is exactly that. So this expected value is determined by a given physics model, standard model, or beyond standard model, or whatever your theory is, determines what is the expected value of this observable y. And in the very same way, in machine learning, what typically is doing, we are specifying is what is the function of x that is giving the expected value of this observable I am studying. And this may be given not by a physics model, but for example, by a statistical model, by a neural network, or whatever other model. So this is important to keep in mind because it is easy to get lost in this. What we are doing always here is to first specify probability distribution of your data. Second, specify as a function of your input what is the expected value of this random variable that you are studying. It is also probably useful to make this remark here, that I have experience with even with colleagues thinking that machine learning is actually replacing physics, which is totally unfair in my opinion. So, for example, imagine that you have a very complicated theory that you know, like QCD. Okay, but then there you see, okay, QCD is known, so we know the properties of QCD, but it's very complicated to model. For example, imagine that you are going to the strong regime, and then it is complicated to model actually, and to make accurate predictions, of course. And when this is the case, then machine learning can be useful here because it allows you to bypass this modeling or this implementation, if you want, of the physics, the physics law that you know. Another role of machine learning in physics is when the later is actually partially known. Let's say, for example, you are in the context of studying your gamma ray emissions in the sky, and you are actually physically interested in that matter, for example. But in order to study that matter, you need to know what is not that matter, right? What is the background to that matter studies? And actually, the background is the knowledge of the background is limited nowadays. So actually, the background, which is something that you require in order to make a statement on that matter, but you are actually not interested in, which is a nuisance parameter, if you want, of your theory, you can actually model this background in a data-driven way or in a machine learning way. in order to come back to the object of physical interest, which is your dark matter. So here again is a second example where machine learning is like allowing you to complement your physics knowledge instead of replacing the physics knowledge. And last but not least, I mean, we see, for example, in the discipline of condensed matter, for example, that physics can actually be rediscovered by algorithms. So you give some system here with the phase transitions, and then there are papers that actually with machine learning they are able to describe the phase transitions, and then you use these algorithms in order to discover new features of your system. For example, order parameters in your phase transition, etc. So those are like three types of applications of machine learning into physics, where it is for sure a complement to physics and not a replacement of physics. Anyway, this is just I always like to make this point because it is probably something that some people may think that we are actually not doing physics when doing machine learning, which is completely wrong, I mean, in my opinion. Anyway, so statistical inference on the distribution of data, what I am saying about that. So if you have this minimum knowledge on statistics, I'm sure you know about this. So there are two different approaches in order to make statistical inference. The first one is the frequentist approach, where the object of interest is the likelihood. Okay, and here what you are saying, okay, the likelihood here for a model H, depending on some parameters WH, is just the probability distribution of your data, no? That of course depends on these parameters, given that model, no? So you have this object for every, let's say, statistical hypothesis that you do, for every model that you assume. And you, on the other hand, you have a catalog of models. So you may think, okay, I would like to describe my data as good as possible. And I have a catalog of models that I think may be reasonable for doing this task, for this description. So what I would like to do is to actually choose this one of these models, that the one that best describes the data. So so what you do here is to first of all, what you do is to like fit the parameters, or if you want, optimize the parameters of a given model H by maximizing the likelihood. So this is the maximum likelihood estimation of the parameters of some given model H. And actually, when we see in the literature about, when we read about machine learning, what they are actually doing is to minimize a cost function or an error function. But in many situations, this error function is actually nothing but the minus log of the likelihood, if you want. So it is a completely equivalent to maximize the likelihood. So what I'm saying is that in many situations, by minimizing some cost function, what you are actually doing is to compute the maximum likelihood estimate of your parameters. So you do this for every model of your catalog, but how do we choose what is the best model, if you want? So suppose these data points come from a given function plus noise. So you have noisy data in general. They come from some probability distributions, and they are noisy, they are random variables. And then what you want to do is, for example, to model the expected value of this output by imagine that you have this model where this is like a polynomial, let's say, where you have some coefficients for your polynomial, right? Then your data points here in blue that actually came from some underlying distribution whose expected value is the green line. Then you wanted to model this by different degrees of the polynomial. In the first plot is like polynomial of order 0, like a constant, linear model, or some like cubic model, or polynomial of degree 9, let's say. No? So first of all, when you do this for all the models of your catalog, you realize in general that as you complicate, as the model in question is more complicated among the catalogs of models, among the models in your catalog, sorry. If you go to more and more complicated models of your catalog, your likelihood improves more and more, right? On these, let's say, training points, if you want, on this data. So in order to avoid unwanted behavior, like you see here, model H9, which is a polynomial of degree 9, if you want, which is actually passing through all the data points that you see here, but it fails at describing what would be the underlying distribution, which is given by the green line. What the most popular probably strategy in machine learning is to do the following. So what they say is that you are doing overfitting of your data, and in order to avoid this, you divide your data in some subsets. The first subset, you call it training data, with which you train your parameters, or sorry, optimize the parameters of a given model. And then you evaluate how well this fitted model does on the test data, which is some smaller fraction typically of the data that you have reserved for later. So if you do this for each model, and you make the fit using only the training data, so you get for each model the maximum likelihood estimate of the parameters here in this first expression. And then, as a second step, you choose the model that maximizes the likelihood of the test data. So you go to the test data, and then you actually choose the model that performs the best on the test data. So this is if you want the roughly speaking the what people mostly do, at least in the frequentist approach to machine learning, to choose the best model. Then if you do this, you will see that if you plot something like model complexity in the x-axis, here given by the order of the polynomial, and you plot the error in the y-axis. So what you see is that while for the training, as you go to more and more complex models, your error or your likelihood, your error is minimal, or your likelihood is maximum, right? So your error decreases or your likelihood increases. For more and more complicated models, there is some point at which there is some model complexity above which, for the test, you are actually losing your predictions, or your predictions are becoming worse and worse. This is what happened with this model polynomial order 9 here. Okay, that and then you say, okay, here probably in this particular plot, all these models from polynomial of order 3 to polynomial of order 7 or so are more or less equally good, but definitely not polynomial of order 9. There is a common form of the error function, which is the mean square error, that is used typically in this task of, let's say, here, this is a regression task here. And the generic feature is this one that I was just saying, that the training test goes up at some point, while sorry, what I'm saying, error test or error of the test goes up at some point, while error in the training goes down at some point. Always so. So the problem with this is, well, there are many problems, but let's say, what if data is scarce? What if this splitting of the data is actually a luxury? Because imagine that you don't have a lot of data, you have only whatever 10 data points. So if you have 10 data points and you reserve, for example, 30% of the data points to the test, you are only remaining with 7 data points with which you need to feed your models. And this may be inconvenient in the sense that with only 7 data points, I may obtain a poor, let's say, prediction, because I have few data points. So if in the cases where my data is scarce, what I would like to have is a strategy that allow me to propose a good model while using all the data without the needing to split training and test, etc. Because I mean, ideally you use as much information as possible, right? So this is possible in the Bayesian approach, where you just okay, I am assuming you're familiarized with this again. So you follow the Bayes theorem, where you actually here you are trying to estimate the posterior of the parameters of your model here, WH, given the data and the model, of course. And this is given by the likelihood. And then you also need to specify the prior distribution of your parameters before seeing the data. And of course, this the normalization factor, factor here, which is the marginal likelihood of evidence, let's say. And then what you actually do is to compute the parameters that maximize, I mean, in order to fit your data in the Bayesian way, you are actually maximizing your posterior here. Instead of maximizing your likelihood, you maximize your posterior, and then instead of calling maximum likelihood estimate, it's called maximum a posteriori estimate of the parameters. And actually, what happens is very interesting. So imagine that I now go back to my problem of fitting a polynomial of order 9 to this data that I showed before. If I do this without prior, without this new element that I introduce in the Bayesian framework, or if my prior is flat, which is mathematically the same as having no prior, let's say, then what is happening with all the coefficients of this polynomial of order 9 that I'm trying to fit? So the optimum value of the coefficients are given by this column here, this first column here. So you see that the coefficients of the terms of higher degree, for example, the coefficient accompanying x to the 9, is very large. So there are very large coefficients. And what is happening here is a fine tuning among these coefficients in order to accommodate data points. So this is what is happening, and it's actually the result of some singularity that goes in the feature matrix that we will see in the lectures. While if you do use a prior, a non-flat prior, let's say, for the same polynomial of order 9, then look at the second column here. What are the coefficients accompanying all these terms in the polynomial? They are reasonably, I mean, the size is reasonable if you want. And what is happening here is that this prior makes sort of a regularization of large values of these coefficients. And if you regularize somehow the values of the coefficients, then you are actually preventing overfitting. And then even with, let's say, this very simple data set, which is 1, 2, 3, 4, 5, 6, 7, 8. So I think there are 10 data points here or so. You would expect that a polynomial of order 9 would overfit the data badly. This is the case if you don't use the prior. But if you use, for example, a standard normal prior, what you get is a nice behavior here, right? And this is actually something which is this regularization that we will see in the lectures are actually something that people use nowadays. For example, at Google, for example, when they create more and more complex neural networks. Which means more and more parameters. Some neural networks may have 1 million parameters or something like that. Of course, they are using these to go to like a model or to describe complex data sets. But in general, these highly complicated models, machine learning models, they are over parameterized, which means that they don't need all the parameters that they are actually using. However, if you regularize it somehow, it will be able, this highly parameterized model will be able to describe without overfitting some data, some simple data that a priori wouldn't require, or in principle wouldn't require such a complicated model. Then the way to choose the best model in the Bayesian approach is to do this Bayesian model comparison, which is just comparing the evidences. No, so the evidence is like the denominator of your Bayes theorem here. You compare the evidence of the model, and according to, if you want to compare model 1 and model 2, well, you compare this ratio of evidences, which is called the Bayes factor, and then you may have your decision according to what the value you get, or something like that. Again, this is something that we saw in the statistics course, and then I am assuming that you are familiarized with that. So as for the predictions of a new point, as we will see in detail in the lecture, the frequentist approach, once you have fitted your parameters, let's say W star is the value or the optimal parameters, let's say, for a new input x new here, what you would do is to, just set a prediction by just replacing this value of the fitted parameters and the value of the new input to the function that is defined in your machine learning model. Here, in principle, no uncertainties are addressed. No uncertainties on the predictions are addressed. In principle, then you can do other things, but in principle, no uncertainties are already implemented at this level, if you want. And then you, as opposed to that, you go to the Bayesian approach, where you do have a prediction which is much more informative, in the sense that instead of giving a point-like prediction like this one, what it gives you is a distribution, a probability distribution of your prediction, which is called the predictive distribution here. So the predictive distribution for the value of the output at a new input, x new here, given some data D or training data, call it as you wish, then it is just this integral that it is actually like the expected value of the likelihood of the new datum, let's say, right? So you use the Bayes theorem in order to estimate the posterior distribution, and with this posterior distribution, you compute this integral, which is the expected value of the output, integrated over all the possible values of the weights. Of course, this framework allows you to also pick a best fit point or the mean prediction, if you want, which is the mean of this predictive distribution. But since this is a distribution here, then you can compute not only the first moment, which is this one, but also second moment of the distribution, which is the standard, the variance, etc. So you have all the information, right? Once you have the predicted distribution, you can, of course, access not only to the mean and the uncertainties, but also to all the other moments of the distribution. And what is nice about the Bayesian learning is that so the predicted distribution is behaving in an intuitive way, in the sense that you have a mean prediction. Let's say, imagine you have some data point, coming from, secretly coming, if you want, from the red distribution, from the red function, green function. And then you see one data point, and the predicted distribution is having a mean, which is given by this almost horizontal red line. And what is nice here is that the variance of your predicted distribution, or if you want, the uncertainties associated to the output, after seeing only one data point, of course, they grow far away from the point that you have observed, and they become more accurate close to the point that I have observed. And there is some sort of, how we will see in the lectures in detail, there's some sort of a sequential learning in Bayesian, in the Bayesian framework, where now you start adding new points to your observations, if you want, and then you see progressively how your predicted distribution shrinks at the regions where shrinks in the sense of the uncertainties shrink. At the regions where you have observed data points, and of course the uncertainties remain large, far away from the data points, right? So then you have this sort of, for example, in this plot here at the bottom left, you see it with 4 data points, and eventually, if you had enough data points, then you would obtain something more smooth like that. But this is a quite nice result in the sense of it is intuitively reasonable that my prediction is less certain far away from the points that I have observed, and this is something that is possible in Bayesian learning. So about the task of classification, previously we have dealt with some regression here, which is just predicting the output of a continuous variable. In classification here, the random variable here is actually some categorical, so it has either 2 or more categories. For example, signal of background in physics, or I don't know, dogs, monkeys, humans, etc. At Google, let's say. And the way to deal with this is to describe this random variable, this categorical random variable, by some vector of given by the number of classes, if you want. And this will follow some distribution here, which is actually generalization of the Bernoulli distribution. And what we are after in classification is we're after modeling the true unknown probabilities of each class. This is the object of interest. And so we model, for example, P1, we model this as P of C1 given some new value of the input, let's say. And by modeling this, a data set with this distribution, then you are able to draw some like decision boundary here given by this black line and black curve in the plot. And you do this, like you find what is the optimum decision boundary, typically by minimizing a cost function, which is the same as maximizing the likelihood coming from this assumption here. And a common form of error function is this cross entropy, which is given by this. So this cross entropy is maximum, is 0 where when the point is correctly classified, let's say, or where you have like completely determine exactly what is the value of the probability of the observed probability, and then you are able to make a prediction for this red point here, let's say.
Brian?
So what? Yes.
Yes. Hello, Jose here. So I wanted to ask you 2 things before you move on, so I get an idea where we are. So when you were discussing regression, the first point that I want to make clear is that the user or the data manager or there's always a choice to be made, right? It doesn't matter if we go frequencies of Bayesian, we need to choose either a model or a prior. Is this correct, or I misunderstood you?
Yes, I mean, you need to choose a model. You need to parameterize your probability distributions, yes.
So doesn't matter your probabilistic approach, you are always introducing some kind of, let's use the word bias, but not in the technical term. So there's some user input coming in there. And
yes, but not always, as we will see.
Okay.
As we will see later in the course, there is a way to parameterize your probabilities, which is called non-parametric methods, which is actually the way to be I mean, the way we know to avoid this bias, this theoretical bias, if you want. So there is a way to avoid as much as possible your theory bias, if you want.
Okay. So,
yeah.
and the second question is, since you started discussing classification, so the way you discuss it, regression seems that you are only going to do supervised learning because you're always trying to match this, let's say the Y variable is something that you are giving the data. But here in classification, the way you introduce it, it seems to be suited for both supervised and unsupervised methods. Is this correct, or I missed something in the regression, that you can do regression in an unsupervised manner?
You can do regression in unsupervised manner if well, okay, no, but regression, okay, no, I mean, in the sense, if you think about regression as estimating what is the underlying distribution of some data, which is continuous data, which in the case of regression, then you can do density estimation, which is an unsupervised method.
Okay, thank you.
Yeah. Okay, so then in the context of, as I was in the context of classification, then, okay, yeah, I was finishing this slide there. So now let me talk a bit about models. Not all the models, of course. I will just have some very small presentation of a few popular models here, and hopefully applications to physics that we find in the literature. So there is as for the models, there are so-called linear models, and this is in quotation because of the following. So this is considered as a linear model, for example, in which you have a linear combination of functions which don't need to be linear at all. So these phi's are a catalog of functions that you previously specified, which can be, I don't know, polynomials or trigonometric functions or any nonlinear function that you may wish. If you have a catalog of these functions and your prediction is actually built as a linear combination of these nonlinear functions, then this is taken as a linear model in a way. Okay, so here you see it, no, that depending on the basis function that you choose, then you are quite flexible to describe the data you wish, actually. This is, for example, the input in only one dimension. There is also the perceptron, which is, as we saw in the history, no, in the preview, at the beginning of these slides. In the history of machine learning, was probably one of the first or the first model of machine learning, which originally was specific to binary classification. So here, a non-probabilistic model is proposed, where you have a nonlinear function of a linear combination of inputs, right? And here the model, I'm saying that the model is linear because the argument of this nonlinear function J is, G, the argument of G is a linear in the generalized sense that I was specifying previously. And here actually you can represent this equation here in this diagrammatic form, where you have some input variables, so you may have D of them, so this vector X here. And they actually are able they are combined with these weights in a linear way in order to form the quantity A, and the quantity A is just the argument of G. And then you do some prediction here, either -1 or 1. If, for example, in the case of the perceptron, if A is larger or equal 0, you assign it to 1, and in the other way, you assign it to -1. You can consider this as the simplest possible neural network if you want. So the perceptron algorithm actually optimizes these weights by considering only misclassified points. So you see here how during the training, the decision boundary moves given by some algorithm that we will see in detail in the lecture. But the important point I wanted to address here, the important message here is that this is a linear model in the sense that the decision boundary of this classification problem is linear, or this is a hyperplane or whatever. Okay. Another linear model is logistic regression, and it's also for classification, where we are, as we were saying before, modeling these probabilities of some class CK given an input. And there is a way to express this probability, this conditional probability that I am trying to estimate. It is actually always possible to express it in the form of a sigmoid function, sigma A, where A is this quantity. So it is always possible to describe this as a sigmoid function. We will see what is a sigmoid later, but this is just a function that has this behavior, if you want, given by this plot. And if you that the input is distributed as a Gaussian, then you see that the argument of this sigmoid is a linear in X, and in consequence, the decision boundary will be linear in the input space, in the same way as happened with the perceptron. Okay, so logistic regression is something that we will see in detail the lectures as well. And then you may move to nonlinear models, the most popular of which is the artificial neural networks, where it actually was, some say that it was born in 1943, where they were doing this first modeling of the neural activity in the brain, right? And so here, you may use neural networks in order to perform regression tasks or classification. And depending on this, you may choose your nonlinear function to be actually the trivial one in the case of regression, so where g of A is equal to A, or some valid, we will see many of these later, activation function, they call it the G in the case of classification, right? So the neural nets here are following the same functional form as before in the perceptron, in the sense that there is a nonlinear function H here, which is a function of some linear combination of the inputs for every layer of the network. So the hidden layer here, let's say that the output of the hidden layer here, it is just a layer of nonlinearity, if you want, where you form linear functions of your input and you make this nonlinearization, right? So you put this linear input as the argument of a nonlinear function H, and then you do this for every layer. Here there is only one hidden layer, if you want, and then you compute your output as potentially another nonlinear function G of a linear combination of the output of the previous layer, right? This is a case of one hidden layer fully connected, they call it feed-forward neural network, in the sense that you are computing the output in a feed-forward way. So from the input going to all the layers to the output. The way to train neural networks is typically done via a technique called gradient descent. And the gradient descent is the following. So imagine that your manifold, if you want, or if you want the value of your cost function is given by this surface here that it's been trying to show in 3 dimensions here. And the idea is to start in a random position that may be, for example, the top of a hill, and then you try to go to the minimum here. And you try to go to the minimum through this procedure called gradient descent, where you update at each epoch or at each iteration, tau, I mean, iteration given by tau, so you update the values of the parameters depending on the gradient of the function evaluated at this point. Right, so this is more or less what the idea behind that. And again, do not try to understand all these equations here, and this is just a summary of what we will see later in the course. As for these nonlinear functions by the neural networks, in the past they were very popular on this sigmoid, which is this blue one, and also hyperbolic tangent, which is the red one. And they are nice because they are bounded and they are interpretable, but they have some issues with vanishing gradients, in the sense of if you happen to be at, for example, 10 here in the plot at the left, then you see that the gradient of this function is 0, and this creates a problem for the training. And then in order to avoid this, like more recently, some other functions are used. For example, this is so-called rectified linear unit, this ReLU, which is the black, or the leaky ReLU, which is the leaky ReLU version, which is the orange here. Actually, leaky ReLU is one of the most popular right now. But there are tens of activation functions that you can that people use in the literature. I mean, you just go to Wikipedia and then you see this catalog of activation functions. That you should, of course, choose the one that is more adapted to your problem. But okay, I mean, in most applications, these typical functions, they work very well. These neural networks are, as we will see in the lectures, very popular because they are very flexible, or they are, I mean, their capability to adapt to any data set is huge. I mean, and this is given by the universal approximation theorem, which say that a feed-forward neural network with a single hidden layer, but otherwise you have an arbitrarily large number of neurons in your hidden layer, but finite, okay, can approximate any continuous function. And this is something that we will try to demonstrate at least graphically in our lectures. But it is actually something that that would lead you to think that okay, then why caring about other models, right? If I have found this model that is able to approximate, I just need to add units in my hidden layer. If the data set become more and more complex, then that's it. Then the task is sort of straightforward, right? But this is not the case. Anyway, there are other configurations of neural networks as with many more layers. So you go deeper and deeper means that you start with one hidden layer where you have a nonlinear function of a nonlinear function of your input. In two hidden layers, the level of nonlinearity increases by one level, and so on, right? And then you may see diagrams like this one, which is a fully connected network having a lot of parameters, and all of them are connected one layer to the next. Today, in order to do image classification, there are more popular architectures, or more efficient architectures, and based on convolutional neural networks and all the refinements that appear every day in the community. But as I was saying, about the question of have we found the universal machine learning algorithm, the answer is no. Of course, there is this theorem called no free lunch theorem in the 97 applied to data science, which says that for any algorithm, any performance over one class of problems is offset by performance of another class. In other words, I'm saying that, I mean, in the case of neural networks, if you actually use it for a class of tasks, it will not be performing with the same, let's say the performance will not be the same as you wish in other class of problems. So depends on your problem, you will be better proposing another algorithm, which may not be neural network, for example. Okay, nonetheless, as I was saying, there is a large number of problems where neural networks apply, and they produce decent results. Examples of using neural nets. Let me see what time is it, because I don't want to spend, okay, I will probably 5 minutes more, and then I do a small break. So examples of using neural nets. For example, here, this paper of 3 years ago, extracting gamma ray information from distributional neural nets in the CTA experiment. So here is a problem of image recognition and classification of gamma showers versus hadronic showers. Or in the context of condensed matter, here this paper is learning about the phases of matter in the sense of they are classifying the different phases of some material, let's say, as a function of the temperature. And here there is actually no physics input beyond the spin configuration, of course, that you need to in order to build your data set. This is actually more creepy, in the sense of discovering physical concept with neural nets. So this paper that was sounding a lot when it appeared. And here, what they are doing is actually, for example, they extract, they are able to extract the loss, determine the frequency of the pendulum, or the total angular momentum, or I don't know, imagine describing the degrees of freedom of some underlying quantum state like the spins, for example, or even the heliocentric model of the solar system. So the model actually came up with this law that you knew, but was not an input of your problem, right? And here what they are doing is regression and doing inference of a space of latent variables using autoencoder, which is another popular technique nowadays. There is another very popular class of model, or let's say type of model, which is decision trees. And this is actually used in particle physics since many years ago, since at least the beginning of the 90s. In the context of LEP, they use decision trees. And here, the idea here is to find a greedy, is to define a greedy algorithm in the sense that, so okay, we'll see what greedy is later on, but at each step, you choose the optimal variable to make some split in your decision. For example, here you have a number of variables here, and you say, is this variable larger than some value or greater than some value? If this is larger than some value, smaller than some value, then I make another one decision. If it is larger than this value, I make another decision, or I make another split. This is actually the way doctors think, more or less, when they try to discard some bad disease or whatever. They go to the symptoms, say, so do you have headache? Yes, no. So if you don't have headache, do you have this? Yes or no, etc. So you can apply this to scientific data, of course. And this has been applied. I believe that in particle physics, this is probably the most popular. Traditionally, today things are changing fast, of course, but traditionally, this has been the technique used the most in particle physics, in collider physics context, by studying the type of events that you produce at the LHC, for example. Then in classification, you are classifying points, for example, signal and background, etc. Here you use several measures of node purity in the sense of, for example, what is diffraction of points from one class with respect to the other class, this sort of purity, let's say, no? And an example of an application for that is, for example, this one. This is, for example, a colleague of mine 4 years ago, studying invisible decays of the Higgs in production, where here what they do is to optimize the signal to background ratio from, of course, using a set of kinematical variables relevant for your problem. And they use an advanced implementation of decision trees, which is called boost decision tree. So far, all of these models that they have shown are parametric, in the sense that they assume a specific functional form of the probability distribution. And this is going back to the question of Jose, that is this always the case? Well, no. There are situations where there is a poor performance, right? If you assume, for example, that some data is generated by the Gaussian distribution, but this data is not Gaussian at all, then this assumption may give you bad performance in general, right? So instead, what we could do is to estimate the distribution with the data we have at hand, right? And this is what the non-parametric methods do, actually. It is non-parametric, not that there are no parameters here. It is just that these parameters do not fix the shape of the distribution. The shape of the distribution is fixed by the data we have. And as the data grows, the model complexity grows, given by some hyperparameters, let's call it like that. But the whole distribution or the whole likelihood of these non-parametric methods, as we will see in the lectures, are actually a function of the number of data points you have. So each data point in general will have a different contribution to the likelihood of, to the shape of the likelihood of this non-parametric method. And the task here is, for example, to estimate the underlying distribution of some data. Here in this cartoon of two-dimensional data, I just want to say, okay, I would like to see what is the underlying distribution of this data I have here, and there are two approaches to this problem that we will see in one of the last lectures, which is on the one hand k-nearest neighbors, and on the other hand kernel methods. Each of them they work complementary to the other in the sense of they fix one quantity to extract the other, etc. Right? And in the case of non-parametric methods, it's a very powerful technique where, for example, the likelihood, the non-parametric likelihood, if you want, of a given point x here is given by this linear combination of kernel functions. And these kernel functions, as the argument, is just the distance between the input in question and all the points of your data set. And the importance of this is that under quite weak hypothesis, it provides an unbiased estimator of the true underlying PDF. And this is what I was answering to the question by Jose, that this is the best that you can do, in the sense that you have a theorem that ensures you that if you have a large amount of data, as we saw in the previous course on statistics, this is what an unbiased estimator means, is that the expected value of your estimator, I mean, converges to the correct underlying value in the limit of a large data sample. Then it will be unbiased if you have a sufficient amount of data. And as for the kernel function, this may not be unique, so there are many kernel functions in the market, like a Gaussian, I don't know, linear, exponential, whatever. But all of them, they have the characteristic that they actually depend on some smoothing parameter. For example, in the Gaussian kernel, it depends on this parameter h here, which may give you the width of the Gaussian, right? And if you use a very small width, you may have a description here, which is quite noisy, like in this plot here, the one in the top. If you have a too large value of your smoothing parameter, your distribution, your resulting distribution may be too naive or too smooth for the realistic data at hand. So then typically the game here to play is to find what is the optimal value of this smoothing parameter. This is actually a hyperparameter of the model, such that the data is as well represented as possible. Once this PDF is estimated, of course, you have all the information. You have the mean. You can have any prediction of not only the mean, but also the variance, etc. So it is informative in this sense, and it is convenient in the sense of information. So it allows you, in particular, to have controls of your uncertainty. An example of that is something that I worked some years ago, dealing with constraints from dwarf galaxies to dark matter, by modeling the background, the gamma ray background, in this way, in this non-parametric way. And finally, the unsupervised learning model. For example, here I have the unsupervised learning, as I was saying, is like trying to, for example, one of the tasks was this clustering that we were mentioning before. And here, for example, one of the models that we will see is this mixture of Gaussians, where the probability of a point is just a linear combination of Gaussians, here, each with its own mean and variance, or covariance matrix. And the idea here is to, I don't know, to maximize the likelihood somehow. So there, here, just in the plot, you see some progress of what is some of these learning algorithms, where you start proposing the centroids of the two Gaussians to be, I don't know, random like this one. And then you slowly, so you, by following this procedure, you are able to adapt the Gaussians to the data points you have. And at the end of the day, you, I mean, this is actually a point in an iteration, which is close to the final iteration, close to convergence, where you have, as a result, these two Gaussians describing the data in a very good way, let's say. An example of that is, sorry, for example, in the dark machines, platform, where what you want to do is to have to estimate the classes of the data. Sorry, of the point-like sources that you that you observe in your galaxy, let's say. There is another class of unsupervised learning, which is dimensionality reduction. So what I was saying, data that look like a high dimensional, like here at the left, is actually made coming from lower dimensionality, right? So here, instead of 3D, it may be 2D, no? And to find this intrinsic dimensionality here is, one of the techniques is called principal component analysis, which is given by, for example, this plot that we will see later. An example of that was in phase translation again, where the idea is to find the underlying feature extraction, which is just the order parameter. And as a final example, but this is probably out of the scope of this course, is that you may even use machine learning, or at least quantum learning theory, or sorry, computational learning theory, in order to find the ways to apply machine learning to systems, to quantum systems, if you want. So here, the idea is to have distribution-free bounds on the type of data, quantum data that you have, for example, in a quantum computer, right? Okay, so I don't know how much time I spent on this. Almost 1 hour and a half. Let's do, if you want, if you don't have questions, let's do a 6-minute break until past, and then we start with the second part of the lecture. Is there any questions so far? Okay, I don't see any questions. I don't hear anything. So let us make a pause until past.
Okay, thanks.
Thanks. Hello, do you hear me?
Yes.
Yes.
Okay. So let's continue if you want with the second part of the lecture. I don't know if I would require a little bit more time. So depending on you, either we do it a little bit today or tomorrow before 11, let's say. But I will ask you this at the end of the lecture. I mean, by 1 p.m. And another thing is that the notes that I will share, that I will here show online, are not going to be uploaded to the Indigo, because what I'm having here is just handwritten notes. So I don't have this in digital. And so I am just writing this at the in the lectures. What I can do, if you want, okay, what I can do is to share what I am writing today, but what I cannot share is my notes, because this is just a handwritten full of comments, etc. So this is not convenient. But if you prefer, I can just upload what I will be writing today here. I mean, during the lectures. Okay, so let me share some screen. And the idea of this final part of today is essentially to make a reminder of the statistics that concepts that we need in order to understand the course. Okay. So here is just a summary in statistics, right? Summary. Sorry. Summary and statistics. Okay, so first of all, as I was saying, I'm assuming that most of you are familiarized with these concepts, but I just, as a reminder, as a half an hour reminder or something like that, or maybe a bit more, but it is probably useful to have it in mind. Okay. So first of all, useful probability distributions. So here, one of the distributions, probably the simplest one is the one from binary variables. And the distribution of the binary variables is a binary variable is a variable that, for example, can take only two values, 0 and 1. And then here, so here the probability, let's say, imagine that the probability for being x1, you call it mu. Then, of course, the probability for being 0 is 1 minus mu. And then you can describe this random variable, this binary variable, with the Bernoulli distribution, which is just the probability of x given mu, given by mu to the x, 1 minus mu, 1 minus x. This is the basis of binary classification. So this is the basis of binary classification. As we will see. Because, for example, you suppose that, imagine that you have your data set. So your data set D consists of observations of a binary variable 1 to n. Then the likelihood of your data set, I can write it like this. And this is just the product of all the, I mean, assuming identically independent and identically distributed data. This is just a product of all the Bernoullis of all the points. Right. Then, if instead of having, and this is like if you want the object of interest, at least in the frequentist approach. So if instead of binary, imagine that now you have a categorical variable. If you have categorical variables or multinomial variables, call it as you wish, then instead of 0 and 1, you may have 1, 2, I don't know, C, or let me put K, let's say. K possible values, mutually exclusive, of course. I mean, for example, a ball can either be red or blue, but cannot be the two of them at the same time. Then the way to study, the most convenient way, or what we do in machine learning to study these variables, is to parameterize this variable that can be 1, 2, or can be K, etc. To parameterize this variable, so parameterize it in the so-called 1-to-K scheme, or more in machine learning terms, one-hot encoding, right? So, which is that now a point xi will be actually promoted to a vector, and this vector is actually has 1, 2, etc. K, capital K. Okay. So this is a binary vector. Such that if xi is, for example, 3, imagine from all your categories, is it just 3? Then will be described, and you have, for example, K equals 5 categories, but your vector is just 3, is the value 3. Then your corresponding vector here would be 0, 0, 1, 0, 0, let's say. So it is a binary vector where one you have 1 at the position, at the corresponding position, and 0 in the rest. Okay, so this is the way we have. This is the best way we know in machine learning to parameterize a categorical variable. And if you parameterize it in this way, then the probability, the distribution, is the categorical distribution, or generalized Bernoulli. So which is a distribution that converges to the Bernoulli when the number of categories is 2. And the generalized Bernoulli is just, of course, now I am using the fact that I am parameterizing my variable as a vector, and each of these components of these K classes will have an associated true underlying distribution, mu K, right? So this mu K here, sorry, this mu is just the vector of mu K from 1 to capital K, analogous to what mu for the Bernoulli was, but now for each category, let's say. And so the shape of this distribution is product from K1 to capital K of mu K to the xk. Okay. And this is, I mean, note that if I use this, for example, for two classes, if I use this for two classes, then this will be mu to the 0, mu1 to the 0, mu2 to the 1. For example, if x is 0, 1, let's say. But if I have only two classes, of course, this is like a 1 minus, sorry, mu. Let me put it like that, mu times 1 minus mu, right? Because mu1 plus mu2 it has to be 1 in a way. So what I'm saying is that minus mu1 plus mu2 has to be 1. So you can rewrite this in this way. And then 0, 1, which is actually what you would get from a simple Bernoulli. In the case of a variable having 0 and 1. Okay. Analogously, if you have your data set having many predictions, so you have n observations of these categorical variables. Let me put this like this. So I have n observations of this vector because I have a data set with this characteristic. Then, in this case, the PDF, the probability distribution function, is let me put it. Okay, it will depend now not on a single mu, but on a mu for each category, and this will be for the IID data from 1 to n of this generalized Bernoulli one, which is the product from K1 to capital K of mu K x I K, if you want. Where this guy here, this IK here, is what is the value at the event I, or the point data point I, of the kth category, if you want. Okay. Then, so what happens if you compute the log of this, or the minus log of this, the minus natural log, okay, of P of D mu D. So I just compute the log of that, and this is just minus. Now the log becomes a sum. Sorry, the product becomes a sum. K1 to K of IK log of mu K. Okay. And if this is the case, so when one can actually identify this, one can recognize this as the cross entropy loss function. Cross entropy loss function, which is probably the most common loss function used for classification. So then you see here that what people do when doing machine learning for classification, which is to minimize the cross entropy. What they are actually doing is to maximize this likelihood here. Okay, so it is an exact equivalence. Then okay, there are other distributions, but I am not, I mean, this is just a reminder, I'm not entering into details of all of this. For continuous variable, just a reminder, this is a trivial reminder of your Gaussian. So you have a Gaussian. And the Gaussian, let me put it like that. Because since this is too trivial, I will put the Gaussian for multivariate point, or for a variable having some d dimensions. Then, you know, I mean, I hope you are familiarize with this. This is just, I can write this like this. The value, I mean, the distribution, the Gaussian of a point, random point given some vector of means and some covariance matrix sigma. This is just 1 over 2 pi d over 2, where d is the dimension of x here. 1 over the square root of the determinant of the covariance matrix times this exponential, right? So -1, then x minus mu transpose multiplied by the inverse of the covariance matrix, x minus mu. Okay. And this is something that we will use a lot in this course, in these lectures. I hope you know what is the covariance matrix. You know, so the covariance matrix is a d by d matrix. This is the covariance matrix. And the d by d, I mean, this sigma, this is just, I don't know, for example, this expected value of x1 minus mu 1, x1 minus mu 1, and I will put it like this for a reason. Expected value of x1 minus mu 1, x2, sorry. I was transposing, sorry. So x2 minus mu 2, x1 minus mu 1, like that, no? And then you build your matrix, which is symmetric in this way, no? xd minus mu d, x1 minus mu 1, etc. And you do like this with all the rows of your d-dimensional feature space. And of course, the importance of the Gaussian distribution is just coming from the central limit theorem, no? That tells you that in the large data limit, in the large sample limit, all the distributions at some point will converge to the Gaussian. Okay, so then another small reminder that something that we saw in the first part of today in the lectures. So the frequentist approach to inference. This frequentist approach to inference is just relying on the likelihood, and it is to say, so the likelihood of your data D, I put it like this, like let's say a set of parameters, let's say mu, and this is just the multiplication of all the distributions of your data points, right? So here I put this like this because the aim here, as we were mentioning in the first part, is to model mu, right? And I model mu, so for example, I say that mu is a function of some parameters, okay? And then the aim in machine learning is to model this expected value of the variable, which is just mu, depending on the data point, if you want. But this is a predefined function. Predefined function that you may use. For example, a neural network. And then what you do is to compute the maximum likelihood estimate of these parameters by simply maximizing your likelihood, let's say. Okay. In many situations, I will just write the likelihood like a L of the parameters, since the likelihood is just assuming that okay, likelihood, so you have the probability of your data, which is a random data given some set of deterministic parameters. But once you think of it as, okay, I have already observed my data is fixed, then this is just a function of the parameters. Then this is what the likelihood is, essentially. Okay. Then you may do you may do concrete things. For example, so for example, imagine that you have some data like this. So you have one dimension regression problem. I don't know, imagine that you have some points like this, something like that. Okay. And then the idea is to say, okay, I have these observations. My output, this is my output, right? This is what I'm trying to model as a function of my input, right? So the first thing is to assume, so what you assume that y follows, for example, some distribution. Let's say I follow a Gaussian as a function of, let me write it like nicely. So y of x follows a Gaussian, right? Where the mean of that Gaussian depends also on x and on some number of parameters, and of course some like some variance here. Let me assume that the variance is known. Let me assume that I know the variance, for example, given by the measurements of errors of my experiment. Then let me decide to model. So you can model mu as, for example, I don't know, a linear, just a line, right? When you're fitting a line, this is what you're doing. You propose that the expected value of your output is just a linear function. And then what I'm saying here is that your parameters are just A and B, right? If I do look at the data like this, I don't need to go to a neural network, right? I can just fit a line. No? Okay, so wait, I have some chaos here with the paper. Okay, so then once you have assumed this model, then you write your likelihood. So the likelihood of, which is a function of, sorry, the only two parameters that you have in your problem is just 1 to n of these Gaussians, right? Yi, f. So f is just, this is f. Let me put it like this. F, the function of your machine learning model, let's say, but in this case, machine learning model is straightforward. It's just a line. And of course, then if you compute the -2 log likelihood of this is just -2 of the sum, and then you have some constant terms here, and then you have some and then you have the term of interest, which is yi minus, I'm replacing now the function inside the Gaussian, divided by 2 sigma square. Okay. So if you want to maximize this guy, so if you want to maximize the likelihood, is the same as minimize this, no? So you want to minimize this object, right? So if this is equivalent to minimizing, the this error function, right? So this is just yi minus axi minus b squared. And you can recognize this as the least squares fitting. As the least square fitting procedure that we learned in the first year of undergrad. No? Now, for those of you that that need to, I mean, I recommend this to everyone, but for those of you who need the homeworks in this course, I would please ask you to go from this to obtain what is the optimum value of A and B, which in other words is just to get the solution of the mean square of the least square linear model. So I will, you can go from this. It has a, let's say, assignment number 1, if you want. You can go from here to obtain the solution, which is A optimum, which is n sum yixi minus sum times the sum, which is actually what we use in, I don't know, when we do lab in our first year in physics, we use this heavily in order to fit our lines, which is typically the case at the lab, right? Obtain this. And then B is just 1 over n yi minus a xi. Okay. So I don't want to waste time on this because it's a straightforward computation. It's very short, but please do it. So this is the well-known solution, right? So then you see what my point here is. The typical thing that we did in first year undergrad is just to maximize the likelihood. This is the message I wanted to transmit. So once we have obtained, say once we have this vector, this is the optimum the optimum point in the parameter space of your model because it maximizes the likelihood of your data. Then here the prediction for a new point. Well, the prediction for a new point here is just in the sense of what is the probability for this new point. So I have a new input x new here. And what is I wanted to know, I am able to now to compute what is the probability of an output, of a given output, given this new input, given your maximum likelihood estimate, right? So here, for example, here in the problem at hand, this is just A star X new plus B star, no? And this is the expected value of the output at the new input, X new. Okay, so the take-home message here is that this prediction, let me put it like that. This prediction here is a point-like prediction without associated uncertainties a priori. A priori, or let me put it in principle, in the sense that you can do other things, right? And these other things are something that we also covered some weeks ago in the course of statistics. So, for example, a way out. So in the sense of a way to strictly within the framework of a frequentist approach to associate uncertainties to our predictions is by doing bootstrapping. Okay, I'm not covering bootstrapping here because we covered this a few weeks ago, and I am assuming that you are familiarized with that. Is there any question so far? Because at some levels of this development, I am assuming knowledge, but some of you may not be familiarized with this. However, note, I mean, so this probably we didn't say it a few weeks ago, but note that this bootstrapping may not work in situations like the following. So imagine that you flip a coin, right? And the coin is fair, but imagine that you flip the coin 3 times, and the 3 times you get heads to your coin. So now you want to do with bootstrap. You want to find what is the uncertainty on your estimation on the probability for having heads. And the way bootstrap is built, which is by take the maximum likelihood estimate of your observed data, and with this maximum likelihood estimate of your observed data, you can build your generating function. I mean, your likelihood is completely defined in the sense that you can actually use the likelihood to generate new synthetic data, given this maximum likelihood estimate of the observed data. But if the observed data is so is a fluctuation, then your bootstrap is going to be biased, and then of course this is becoming not convenient, right? So the bootstrap works very well if let's say if you don't have important fluctuations in your data. So then there is the alternative of doing the Bayesian approach. So what I'm saying, probably I am not spending. I probably require 10 more minutes for this lecture. So do you prefer to continue with this 10 more minutes just to finish today, and tomorrow we start with a whole new lecture, or we start tomorrow like 10 more minutes in advance? What do you think? I'm just having 2 other things to say. In my opinion, yeah.
We can continue.
Okay, so if everyone can do it, I just require 10 more minutes, and then I will finish with the story. Okay, thanks. So what I'm saying is that in this, what is the alternative to doing bootstrap? So actually, the alternative is the way to the most principled way to address the uncertainty estimation in a prediction, which is going going Bayesian, right? So then alternative here is to Bayesian approach. So in the Bayesian approach, you rely on the Bayes theorem. I'm not writing the Bayes theorem again, but what I'm writing again is the predictive distribution of your, the distribution of your prediction, which is called the predictive distribution here. So the final, if you want, the final aim, typically, no, is the predictive distribution, is the estimation, right, of the predictive distribution. So predictive distribution again, I write this again, I wrote it in the slides, but it is important for you to have it clear, just in your heads when you go home, or you are at home, sorry. Okay. Is to write what is the probability of the output at the new point, given some data I have observed. So some data I have observed. This data, this is some, let's say, two-dimensional data set that is called that you can take as your training data set. So you have inputs, and for every input you have observed an output. So this is a matrix. This is a capital X here. It's a matrix, and then you, for each point in this data set, you have an output, and I collect these outputs in the vector Y here. So what I'm saying is that the way to estimate this is by integrating over all possible values of the parameters of your model. And when you integrate, what you need to integrate is the likelihood of the new point. Okay, weighted by the posterior distribution of your data. So this is just the posterior distribution of your parameters, of your model parameters, and this is the likelihood of Y new, let's say. So, for example, what you can do, for example, is to say, okay, I have a neural network predicting what is exactly the probability of a given output. For example, in a classification problem, the probability of some class given some input. This is exactly what is the output, the model, what gives you the machine learning model, neural network, whatever. And so you can replace this here, like being the output of your classification of your classifier. And that, of course, the output of your classifier, will depend on some number of parameters. And instead of replacing here the maximum likelihood estimate of these parameters, that would be the frequentist approach, then what you do is to marginalize it by using the posterior distribution. Okay. So then here, of course, the way, once you have, what I'm saying is that once you have access to this, so one can compute the corresponding second moment, no, or the variance of this distribution in order to estimate the uncertainties of the prediction. Okay. All right, so there is a very important result that I want to share with you again. This is probably, it took me like, okay, some pages of algebra. So it is a result which is probably straightforward to get, but it's not that short to get. I will state it here, and again, I will require for you to think on how to get this result. So actually, it is in the Bishop book, what I'm showing now. So let's say a raw proof of what I'm showing now is a Bishop. So again, for the students, if you try to obtain this result, that would be good. And this is the following. So assume some data, right? Assume some data here about I don't know, an observable y, and then take it as Gaussian, as following a Gaussian distribution, but not any Gaussian. So take this distribution to be, depending on some parameters, to be a Gaussian, where the expected value of your output depends on your input in a linear way. So so this is capital X here again, times a vector plus b, which is the independent term in your linear model. And then let me put the covariance matrix like this. So in other words, this is the inverse of the covariance matrix. Okay. This is by some called the precision matrix. So imagine that you have this data here, and that you have assumed that your data is coming from a Gaussian distribution whose expected value behaves linearly with respect to the input. And then assume that the parameters follow a Gaussian as well. So you may interpret this as I don't know, as a prior on your parameters. Okay. So the prior will be have this shape. So just have a vector of the mean vector of your prior, and another precision matrix, the corresponding precision matrix, or if you want, the inverse of the corresponding covariance matrix of your prior. So you have these two suppositions here, these two assumptions here. The question is, so the question here is, what is the conditional distribution of the parameters given your output? In other words, this is the posterior. And second question, what is the marginal? In other words, the denominator of your base theorem that you are familiarized with, I'm sure. So this is the evidence. So the idea is that with this information of the likelihood and the prior, you be able to compute the the mean, the posterior and the marginal. Okay. And the correct answer is the following. I am showing here the answer because the answer has is intuitive at some point. So let me write in red here another assignment. You don't need to have this for tomorrow, okay? It's just during the whole lecture, if you can work out this computation, that would be nice. So the answer to this is the following. So the marginal, so the probability of the data, once you have fixed your model to be a linear model, is also a Gaussian. And it's a Gaussian with the following expected value, expectation value, mu plus b, and with the covariance matrix, which is a little bit less like intuitive, but it is at the end of the day. So this is capital X, precision matrix, and so I'm showing this because of the following. So you see that the marginal here has the same functional form as your likelihood. It is just that the weight, no, the vector of weights of parameters here are replaced by the mean given by the prior. So there you have, it's just an easy way to remember that. So is that when you have two Gaussians in the sense of a Gaussian likelihood and a Gaussian prior, if the model is linear, and this is a strong if, for the linear model, then you will have a Gaussian marginal or a Gaussian evidence whose expected value is given by this. So it's exactly the same model has a likelihood where the weights are replaced, the parameters are replaced by the mean coming from the prior. Here as well is more or less intuitive in the sense that the covariance, if you want, so this is a covariance of the data part, no, the covariance of the data here. So the marginal, if you want, has a covariance which is larger than the covariance of the likelihood. This is intuitive because you are multiplying prior times likelihood, and then the covariance, the resulting covariance is larger. So it is the covariance plus a term which takes into account the covariance of the prior given by this precision here. Okay. And the other is for the posterior. The other answer is for the posterior of the parameter. So given your observed data, this is again a Gaussian. Okay. Then a Gaussian whose mean is the following. So sigma, I will say what sigma is later. This is a transpose of X precision matrix X minus B plus this time, and the covariance matrix sigma. So what I'm saying is that sigma is the covariance. So this is the covariance of this Gaussian. And sigma here is just this expression, which is also intuitive in the sense that it's a covariance that takes into account the covariance of the likelihood and the covariance of the prior. Okay. As we'll see tomorrow, this expression is actually reducing to least squares in the case of a simplest linear model that was the first assignment. but it is this is an important result that we will use during the lectures, and again, if you could work it out going from here to here, that would be awesome. Anyway, so I am already 20 minutes out of time, so I think I will stop here. Is there any question for this first lecture of today?
I have one question more about like a system of exercises. Will you be possible to put somewhere all the exercises which we can do day by day, or? Yeah.
I was not planning to do it, but if you think it is convenient, I can update the Indico with the assignments. The thing is that how do I describe the assignment? Because assignment is sometimes. Let me see, what was the first assignment? The least square. Yeah. I can describe it at Indico, the assignments in words, but I don't know how to put equations there. But okay, I will try to do something. Yes. Okay.
Okay, thank you.
Any other question? Okay, if there is no more questions, then let's resume tomorrow at 11, because I finished essentially the second, the first lecture. Let's resume it for tomorrow at 11, and nothing. Thanks for attending.